So today let's do a physics-based physics simulation. So basically we're just going to take a recording from AR and then transmit it over a WebSocket and then put it back into AR, and we're going to use a pendulum in particular. And so this will allow us to do some neat stuff where we can do some math with the information that we get from the pendulum, and it'll also allow us to kind of create a simulation of, it'll be fun. So when you're combining two AR scenes, there has to be some sort of way of reconciling the origin difference because they both won't start at the same origin. And one way of doing this is just physically put them in the same origin. So that's what we're going to be using today. But in the future, hopefully we can look at other methods. So things like using an anchor or using a marker on one phone to get the difference in the origins. And those are all important things for being able to create some sort of shared reality. But for today, we're just going to literally try and start them as close as possible to the same position. And that'll allow us to have a synced scene. I also wanted to be able to capture all of the raw information from this. So in particular, the positions and acceleration pieces of information within the reference frame of the world. So it is kind of interesting to think about because all these measurements are initially taken within the reference frame of the phone, but then that's corrected to be the local Earth area becomes the reference frame. So that's something that's just like weird to think about. So because we're doing pendulums and we have a bunch of information, I thought it'd be really fun to look into whether we could just show energy conservation. We do have a really messy system because I didn't really try and isolate any of the information. So like we were putting our pendulum on a tree that had quite a bit of bounce to it. There was not a lot of rigidity. So we kind of have an extra spring in there. So there's a bunch of extra things going on. We have some like weird rotation stuff and whatnot, but I just wanted to see how close we could get to energy conservation. So with energy conservation, there's kind of these two equations, potential energy, kinetic energy, and there's a trade-off between the two. So kinetic energy is the whole half of mv squared equals kinetic energy. And then we have the potential energy, which is mgh. And so if we set those two equal, we can cancel out the m and we can move the half onto the other side. And then g in this case is the gravitational constant. So we have this kind of about 10. And then the height is basically going to be our y variable in augmented reality. And then we have our velocity, which is going to be the kind of length of all of these velocities combined. You have to do that whole like Pythagoras theorem stuff. So yeah, basically if we combine these two graphs, we should end up getting something that looks kind of like energy conservation. So when you do this whole thing and you look at the two graphs, you end up seeing that they kind of are a little bit of a mirror of each other. And so that's a good sign that we have something going on here. There is a lot more noise in the velocity here than you would expect. And looking into it a little bit more, it's very easy to tell that that noise comes from our differences in time. So we can see that that actually has a lot of noise in it. So if we wanted to do some sort of smoothing function, we can smooth this out a little bit. So if we use a cleaner set of data, you can start seeing the signal a lot clearer. So we have these two different signals here. So the result that we have is still pretty noisy. And so one of the things that you can do to clean up the signal even more is by using Fourier transforms. Although anything past this point is we are starting to get into that range where you're starting to do so much number crunching that you have to start getting a little bit careful that you're not just removing things of importance. So anyways, using the Fourier transform, you can kind of do a Fourier transform that gives you some sort of frequency spectrum. And then you can actually remove portions of the frequency spectrum that will remove either lower bound frequencies or higher bound frequencies. And that way you can get kind of the frequency that you expect. So because both of these graphs have very clear frequencies attached to them, you can kind of remove all the other frequencies and just use that information instead. So now we're doing some frequency isolation stuff where we're doing high and low band filters. And then when we get that back, we get a much clearer signal, although there still is some mess to it and it's not as clean as we would. There's still even now, after we've done all this number crunching, there's still some extra frequencies and height differences that I can't entirely explain, but we had a really messy system. So I think it's good. So I'm just having some fun with like Python and whatnot, but sometimes in the future it would be kind of fun to do this with a lot more precision. So we're going to make two scripts for this video. So the first one is a WebSocket listener. And so this basically does what we were doing in the last one with the WebSocket desktop, except for rather than updating the cube and putting it back into a 3GS scene, instead we are putting it into a webxr scene. And so that kind of reprojects it in. And that's just a simple little change in the script. So it's not very big. We're also doing something where we're plotting and saving all of the information from the WebSocket. And so with this, we need to use chart.js, and then we have to build out a few different graphs. We've done this previously. Basically, you just give all the information about the graph and you attach it to a canvas, and then the canvas just automatically updates whenever it's given new information. So we want to record all of the positional information, all of the velocities, and all of the accelerations. So we have all that information available. And we are just going to kind of be using the definition of a small change in position equals a velocity, a small change in velocity over time So now we just create a set of these graphs. Then we have to do an updating function. So this is what happens when we want to update our function. Next, we'll go to what happens in our channel. So we have kind of a very similar setup where we have a channel name, and then that gets added to the desktop WebSocket so that we're connected to that WebSocket. And then we are going to listen for messages on that WebSocket. So the next portion is basically what happens with the information we get from the WebSocket. So we push a bunch of information into our different values that we've initialized earlier. So we're just kind of keeping arrays of these numbers. Then we are updating the graph for them. Then we have to go into velocity and acceleration. And so we are going to be using the straightforward difference in position over difference in time equals velocity, and difference in velocity over difference in time equals acceleration. And so we'll just be using those pieces of information to create our velocity and acceleration graphs. We also have to do some things where we add the time together so we get a proper time difference. And then that's pretty much all we have for all of the different graph information. Next up is we want to be able to save all that information so that we can use it later on. So in order to download all of the values, since we have stored it in an array, we can really easily stringify that in JSON and then just add that text into a file and then save that file. And then we'll just kind of remove all of the extra information so we can do this more than once.